So today we will start chemical kinetics. So we first discuss basic kinetic laws. First we will discuss law of mass action. This law states that at a given temperature the rate of reaction is directly proportional to the product of the molar concentrations of the reactants. For example, suppose A plus B gives 2AB. So according to the law of mass action, the rate of the reaction can be written as rate is K is a constant term, it is called rate constant, is concentration of A times concentration of B. And then what is the rate law? So consider a reaction, small moles of A, reactant A plus B moles of reactant B and C moles of reactant C gives products, and the rate is given by minus dx by dt is K times A to the P times concentration of B to the Q times concentration of C to the R, where P, Q and R are the powers of concentrations of reactants A, B and C, and they are determined experimentally, may or may not be equal to A, B and C. The rate law can be defined as the mathematical expression which denotes the rate of a reaction in terms of molar concentrations of reactants with each term raised to some power, like before. Okay, so you see the molar concentration of A raised to the P, molar concentration of B raised to the Q and molar concentration of C raised to the C gives rate of the reaction. So with each term raised to some power which may or may not be the same as the stoichiometric coefficient of the reacting species in a balanced chemical reaction. So if you look at this balanced chemical reaction, here A moles, small A moles of reactant A, small B moles of reactant B and C moles of reactant C, they react and they give products. But if you see the power here, so molar concentration of A is P, molar concentration of B is Q, molar concentration of C is R. So this P may or may not be equal to A. Similarly, this concentration of B raised to the Q may or may not be equal to small b, and this R, concentration of C raised to the R, may or may not be equal to C. Then we discuss order and molecularity of a reaction. The order of a reaction is defined as the sum of the powers to which the concentration terms are raised in the rate law equation to express the observed rate of reaction. So for the reaction, above reaction A plus B plus C gives products, the rate is given by minus dx by dt K A to the P times concentration of B to the Q and concentration of C to the R. So for the reaction, the order, if we say the order is N is P plus Q plus R. So we need to add the concentration of A plus concentration of A to the P here. So we need to add P plus Q plus R. So we need to add the powers of the concentration of the reactants. When N equals to 1, it is called first order reaction, N equals to 2 is called second order reaction, and so on. Now what is molecularity? Molecularity of a reaction is the number of reacting species, molecules, atoms or ions which collide simultaneously to bring about a chemical reaction. For example, H2O2 gives H2O plus half O2, this is unimolecular reaction. 2HI gives H2 plus I2, this is bimolecular reaction. So molecularity of a reaction can be calculated from the stoichiometry. You see the stoichiometry here, stoichiometry of H2O2 is 1, similarly stoichiometry of HI is 2. So the molecularity of a reaction can be calculated from the stoichiometry, but order is an experimentally determined quantity. So order from the stoichiometry, you cannot predict the order of the reaction. So order is an experimentally determined quantity. So we move to integrated rate laws. So first is zero order reaction. So consider a zero order reaction. So reactant R goes to product. So rate of the reaction is minus d concentration of R by dt. So minus sign says that okay, with time the concentration of R decreases. So t is the time here. So, this equals to k to the r to the 0, r to the r raised to the 0, because this is 0th order, this is the order, so 0th order reaction, so we write k. So, dr, d concentration of r gives minus k dt. So, we just cross multiply here. So, minus d concentration of r gives minus k dt. Now, if we integrate both sides, so we get dr, d concentration of r minus k concentration of dt. So, we get concentration of r minus kt plus c, c is the integration constant. So, we can calculate the value of integration constant c by putting t equals to 0. So, at the beginning of the reaction, or at the start of the reaction, for example, the initial concentration of r is r naught, okay, here at time 0. Then the equation, so if we put time 0 here, so minus k times 0, it becomes 0. So, the integration constant c becomes r naught. So, if we substitute the value of r naught, or the absolute value of c as r naught in equation 1, so we can write r concentration of r is minus k t plus r naught. Okay. So, if we rearrange this, we can calculate the rate constant k is concentration of r naught minus concentration of r by t. Now, if we plot concentration of r versus time, okay. So, if we see this expression here, if we plot concentration of r versus time, so we get a straight line. It is like y equals to mx plus c. So, c is, so here intercept is r naught. So, when t goes to 0, when t goes to 0, so if we extrapolate this point here, we get r naught. So, this will be the value of r naught. So, we get a straight line with negative slope here. So, from the slope we can calculate minus k. So, slope is nothing but minus k here. So, from the slope we can calculate the rate constant. Okay. Now, instead of here we are plotting the concentration of r or reactant as a function of time in moles per liter. If we plot rate versus concentration of r, okay, if we plot rate versus concentration of r, so if you see rate is given by this expression here. So, rate is k r raised to the 0. So, it gives you k. So, rate is actually the rate constant. Okay. So, there is no change. So, as time progresses, okay, so since rate, if we plot rate versus r, so we get a straight line. So, there is no change in rate as if we change the concentration of r. So, this is for 0th order. Now, we move to first order reaction. For a general first order reaction, the rate of the reaction is given by minus dr by dt equals to k r raised to the 1, like before. For 0th order reaction, it was r raised to the 0, but for first order reaction, it will be r raised to the k times r raised to the 1. So, if we rearrange it, means if we take r this side, so we get dr by r gives minus k dt. Like before, if we carry out the integration, we get ln r is minus kt plus c. Again, c is the integration constant. We can calculate the value of c when t goes to 0. So, at t goes to 0, concentration of c is ln r naught. R naught is the initial concentration of the reactant. Okay. So, like before. So, therefore, if we substitute the value of c by ln r naught, we get this expression. Ln r is minus kt plus ln r naught. So, if we rearrange this one, so we get ln r naught minus ln r. So, if we are taking ln r this side and kt this side, so you get kt. So, ln r naught by r gives kt. So, the value of k is 2.303 by t log, here log is 10 base. So, base 10, so you get r naught by r. And equation 2 here, so we can also write r naught by r is e to the k kt. So, we get r naught by r is is e to the kt. If we do it like before, so we get basically r naught by r is e to the kt, and if we rearrange this one, we get at r is r naught by e to the kt, and so we get this expression. Now, if we plot concentration of r as a function of time, so what do we get? So, the e, it is e to the minus kt, k is the rate constant. So if we plot a concentration of r versus t, the concentration of r will decay as time progresses, and it will decay as exponentially. So we get exponential decay of concentration of r as time progresses, right here. So you can see that concentration of r when we plot versus time, we get exponential decay of concentration of r. Now if we plot ln r versus time, so we have ln r here. So if we plot ln r versus time here, ln r versus time, if you see, so we get a negative slope, right? So as time progresses, ln r will decrease, and when t goes to 0, so ln r becomes ln r naught. So this is the intercept, this is y, this is c, and this is mx. So from the slope we get the value of minus k. Okay, so we get r. If we plot ln r versus time, so we get a straight line with a negative slope, and the slope is nothing but minus k here. Okay. Now if we plot 1 by r versus time, so 1 by r versus time, if we plot, what do we get? So we have r is r naught e to the minus kt. So 1 by r, concentration of r, gives 1 by concentration of r naught times e to the kt. So if we plot 1 by r versus time like here, so it will increase. Okay, so 1 by r will increase exponentially, right? So it will be an exponential increase curve. Now if we plot a rate versus concentration of r, so if we go back and check, so rate versus concentration of r, if we plot, so it will be again a straight line passing through the origin, right? So this is y, this is the rate. So y is mx plus c is 0 here. So we get, if we plot rate versus concentration of r, okay, rate is in y axis. So you see the y axis, and this is the x axis, and the slope gives you k. So if we plot rate versus concentration of r, we get a straight line, and the slope of this curve gives the rate constant. Then we discuss second order rate reaction, like first order rate reaction. So for a general second order reaction, rate of the reaction is given by rate is minus d concentration of r by dt equals to k r raised to the 2. So again, like before, we do the integration. So we take r raised to the 2 this side, dt this side. So if we do it, so we get d concentration of r by r concentration of r square is minus k integration dt. So we get minus 1 by concentration of r is minus kt plus c. Again we get the value of c when t goes to 0. So if we consider t goes to 0, so 1 by so concentration of r becomes concentration of r naught. R naught is the initial concentration of the reactant. So now if we substitute the value of c from here to this expression, so we get minus 1 by r is kt minus 1 by r naught. Okay. So basically what we get here is t. Okay, so we get the value of t is 1 by r minus 1 by r naught. So there will be a minus sign here that is missing. So anyway, so this is the value of the rate constant. Now if we plot concentration of r versus time, what does the plot look like? Okay, so we are plotting concentration of r versus time. Okay, so we get an exponential decay, right? And if we plot 1 by r concentration versus time, so we get the value of 1 by r will increase with time and it will be a straight line like this. Okay. Now, if we plot ln r versus time, so the value of r is exponential decay. So, if we take ln, okay, so ln versus, so we get similar kind of plot here. And if we plot rate versus concentration of r, so rate versus concentration of r raised to the 2, so we get this kind of plot. So, these are all schematic plots. Third order reaction, for a general third order reaction, the rate of the reaction like before is rate is minus dr by dt gives you k raised to the 3. If we rearrange this one and do the integration, we end up with this expression minus 1 by r raised to the 2 is minus kt plus c. So, for third order general expression third order reaction we already discussed. Now if we see the value of c, how we will get it. Okay, so this is the expression we end up with. Okay, so the value of c, so when t goes to 0, so we get c is minus 1 by r naught raised to the 2. So if we go back and check, okay, so you just we do not need this one. So we will start third order reaction from here, and then we get at t goes to 0, the value of c is this. Now you substitute the value of c from here to here like before, we arrived at this expression. So the rate constant k is 1 by 2t times 1 by r raised to the 2, concentration of r raised to the 2 minus concentration of r naught raised to the 2. So if we now plot concentration of r versus time, okay, again we get this kind of plot, but when we plot 1 by concentration r raised to the 2, if we plot, so we get a straight line with positive slope like this, and then if we plot ln r, so we get versus time, we get this kind of plot. Okay, and when we plot a rate is here. So rate is here. So if we plot rate versus concentration of r, so we get this kind of plot. Okay, so these are the plots for the third order reaction. So this is the third order reaction. Next, we will discuss half-life period of a reaction. So the time during which the concentration of a reactant is reduced to half of its initial concentration is known as half-life period of a reaction. So for zeroth order reaction, so basically what is happening here is, so when r becomes r naught initial concentration of reactant by 2, so we get half-life. Okay. So we will substitute concentration of r by r naught by 2. So for zeroth order reaction, this one we have got so far. So when t is t half, concentration of r is r naught by 2, as I said. So if we substitute, so we get k is r naught minus r naught by 2, because now concentration of r is concentration of r naught by 2. So if we substitute it, and t is now t half. Okay, this is the half-life period. So we get t half here. So we get t half is concentration of r naught by k. So this is the expression for half-life period of zeroth order reaction. Now for the first order reaction, the half-life is like this. So the rate constant for the first order reaction, we got this expression, and now when at half-life t is half, t is t half. So again concentration of r is concentration of r naught by 2. So if we substitute it, we get 2.303 by k log 2. So if we carry out this one, we get t half is 0.693 by k. So this is the half-life period of the first order reaction. Okay, so now we discuss half-life period for the second order reaction. The rate constant for a second order reaction, we got this expression, Kt is 1 by concentration of R minus 1 by concentration of R naught. So at half-life T is T half, so concentration of R becomes concentration of R naught by 2. So Kt half is 2 by concentration of R naught minus 1 by concentration of R naught, so we get basically 1 by concentration of R naught. So this is the value of T half for the second order reaction. So you can see Now, if I go back and look at the different expression, we can see the T half here. Okay, so T half is concentration of R naught by K, right, by 2K here. Okay, so here R naught is in the numerator. Now, if we look at this one, concentration of T half of half-life period of first order reaction, it is independent of the reactant's concentration or initial concentration of the reactant. Here T half is directly proportional to the initial concentration of the reactant, but this is for the 0th order. For the first order, T half does not depend on the initial concentration of the reactant, whereas for the second order reaction, it is inversely proportional to the initial concentration of reactant. So, what we discussed here is, so for the 0th order reaction, T half, so for 0th order reaction, half-life T half is directly proportional to concentration of reactant at time 0, or T half is proportional to the initial concentration of the reactant. So, this is for 0th order reaction. Okay, so for 0th order reaction, the T half value of T half is proportional to the directly proportional to the initial concentration of the reactant. For first order reaction, T half is independent of initial concentration of the reactant. Whereas for the second order reaction, T half or half-life is inversely proportional to the initial concentration of the reactants. Now, if we plot for the 0th order reaction, as I mentioned, it is directly proportional to the initial concentration of the reactant, and if we plot T half versus initial concentration of the reactant, it will be a straight line, and the slope will be passing through the origin, and slope will be 1 by 2K, right. So, this will be the slope is 1 by twice K. This is for the 0th order reaction. Now, for the first order reaction, so as I mentioned, T half is independent of initial concentration of the reactant. So, even if we increase the initial concentration of the reactant, the value of T half will not change, right. Again, it will be a straight line, okay. It will be a straight line, okay. So, you can see the value of T half, okay. As we increase the concentration of initial concentration, here initial concentration is A naught, so we are writing R naught everywhere. So, R naught, if we plot 1 by R naught versus T half, okay, so we get a straight line, but as we increase the concentration of R naught, there is no change in the value of T half. Similarly, for second order reaction, now if you see the second order reaction, T half is 1 by K concentration of R naught. So, if we plot T half versus 1 by R naught, if we plot T half versus 1 by R naught, we get a straight line, right. We get a straight line like this. Okay, this is y, and passing through the origin, okay, y equals to mx, and the slope is, what will be the slope of this straight line? Slope will be 1 by K, right. So, from the slope, if we plot 1 by R naught versus T half for second order reaction, from the slope actually we can calculate the value of rate constant. Now, how do we determine the order of a reaction? The following methods are are commonly used for determining the order of a reaction. The use of differential rate expression. According to this method devised by Ventov, the rate of an nth order reaction is given by this. So, if the order is nth, so Kn is the rate constant C to the n. So, now if I take the log, so we get ln R is ln Kn plus n ln C. Thus, if the double logarithm plot of rate versus concentration gives a straight line. Now, if we plot ln versus ln C, right? If we plot ln R versus ln C, we plot ln R versus ln C, so we get a straight line, right? We get a straight line with a slope here. Okay, so from the slope basically we get ln K. Slope gives n, slope gives n, and the intercept gives this, the intercept, because this is y is c and this is m and this is x. So, n is m, this is x, c and this is y. So, if we plot y versus x, so from the slope we get the value of n, or degree of the reaction, okay, order of the reaction. So, we get order of the reactions from the slope. So, then the slope gives the value of n and the intercept gives Kn, right. Also, if R1 and R2 are the rates of two different reactant concentrations C1 and C2, then R1 is minus dC1 by dt, right, and R2 is minus dC2 by dt. So, for R1 we get Kn C1 to the n, and for R2 we get Kn Cn C2 to the n. So, we get R1 by R2 is C1 by C2 raised to the n. So, if we take log, so both sides, so we get ln R1 by R2 is n ln C1 by C2, oops, n ln C1 by C2. So, the value of n, okay, this n is the order of the reaction, you see n is the order of the reaction. So, we get n is ln R1 by R2 by ln C1 by C2. Then we can also calculate order of a reaction by half-life method. So, T half for 1 is T half for 2. So, we get A2 by A1 to the n minus 1. So, T, if we take log both sides, we get ln T half 1 for by ln T half 2 gives n minus 1 ln A2 by A1, and from there we get n is 1 plus ln T half 1 by ln T half 2 by ln A2 by A1. So, this method, this half-life method was suggested by Oswald. So, from there also, from the half-life method also, we can calculate the order of a reaction. Okay. So, because here if you see the value of T half, okay. So, if you see the value of T half here, so value of T half for 0th order reaction, okay. So, if you go back and check for the 0th order reaction, the value of T half is concentration of R naught by 2K. Right. So, this is your concentration term is there by 2K, right. And if we see this expression here, T half for 1 is 1 by A1 to the 0 minus 1. So, you get A1, and then you have the constant term here at 2K. Okay. So, actually this expression comes from here. Okay. Similarly, this is for first order, this is for 0th order, this is for 0th order reaction. And for first order reaction, T half is independent of concentration, right. We have just seen. So, here also if you plot, if you see, so from this expression, if we put n equals to 1, for n equals to 1, you can see that T half is basically a constant term. So, is constant. So, this expression again is valid for all these 3 different order of the reaction we consider. Okay. So, this is the general expression for half-life, for the calculation of order of a reaction from the half-life period. So this method was suggested by Oswald, and the determination of half-life of a reaction at two different initial concentrations lead to the determination of N. So A2 and A1 are the two different initial concentration of the reactants at two different times. Then we discuss collision theory. The collision theory explains how chemical reactions occur and why reaction rates differ for different reactions. This theory is based on kinetic theory of gases and assumes that, so these are the assumptions of collision theory: molecules are hard spheres and are impenetrable. Okay, so they cannot penetrate each other. Reaction may occur only when molecules approach and collide with each other. Colliding particles must possess kinetic energy equal to or greater than the activation energy to overcome the energy barrier and react. Molecules must collide with the proper spatial orientation for bonds to break and form new products. Only a fraction of total collisions results in reaction. So all the collisions will not result in the formation of products. These are effective collisions, meeting the energy and orientation criteria. The rate of reaction is proportional to the number of effective collisions per unit time. Now let us consider a reaction in which molecules are considered to be rigid hard spheres with no forces of attraction and repulsion. So there is no forces of attraction and repulsion, so molecules are considered as rigid hard sphere. So rate of reaction can be given by this expression. So rate is ZAB e to the minus Ea by RT, where ZAB refers to the number of collisions that occur per unit volume per unit time. It is also referred to as collision density. The number of collisions per unit volume per unit time in such reactions are given by this expression. So this is the expression for ZAB. So rate is ZAB times e to the minus Ea by RT, and the value of ZAB is sigma 8 kT by pi mu to raise to the half, and then Na times Nb, where sigma is the collision cross section and it represents the closeness of approach for molecular collisions. So this is the sigma here. Okay, so this is, you can see it here. So sigma is pi d square to the AB, where dAB is dA plus dB by 2. So this is the diameter of molecule A and this is the diameter of molecule B. From there, so dAB is nothing but average. If we take the arithmetic average of dA and dB, we get this value. So dA and dB are respectively the diameters of reactants of molecules A and B. So we get dA here, and if we substitute dAB here in this expression, we get the value of sigma. So this is the area of sigma, is the area of the cross section, and 8 kBT, kB is the Boltzmann's constant, by pi mu to the half is the average velocity of the molecules, and mu is the reduced mass. So we know what the expression for reduced mass. So reduced mass is Ma, means mass of molecule A times mass of molecule B by mass of molecule A plus mass of molecule B, and Kb is the Boltzmann constant, and as I mentioned, Ma is the mass of a single molecule. Remember, this is for single molecule A, and Mb is the mass of a single molecule of B, and Na and Nb are the respective number densities of molecules A and B. Number density, you know, number density is number of molecules per unit volume. So number density has unit of volume to the minus 1 or length to the minus 3. So the unit of number density is length to the minus 3. Okay, so number of molecules is number, there is no unit of this one, or numerator, and denominator we have the volume term. So you get number of molecules, so N by V basically here. So you get unit of number density is L to the length to the minus 3 or meter to the minus 3. Now we discuss how to derive the rate constant. According to classical theory, classical collision theory, hard sphere theory, rate of reaction as given by equation 3. So this is the equation 3 here. So rate of the reaction is this one, depends on collision density and exponential factor, or one can simply say the rate of bimolecular gaseous reactions depends on collision frequency and its probability of success. So consider this reaction, A plus B goes to product. So rate is minus dNA by dt equals to kNA to the Na times Nb. This is bimolecular gaseous reaction we are considering. So A and B we are considering. So what is the concentration of A? Concentration A is the number of moles of A by Avogadro number, and concentration of B is number of moles of B by Avogadro number, where Na is the Avogadro's number. So minus dNA by dt is K times Na square. So if you substitute the value of Na and Nb by this, so we get K Na square, Avogadro number square, times concentration of A times concentration of B. So we get minus Na dNA by dt is N square A K Eb, right? So finally we arrive at this expression, minus d concentration of A by dt is Na times K, then concentration of A times concentration of B. Okay, so basically this expression is, we get minus d Na by Na, so by dt, this side. So you get minus dNA by dt is this one. So this is nothing but concentration of A. So we get concentration of d minus d concentration of A by dt is Na times K times Ab. Now substituting the expression of collision density from equation 4 in equation 3 along with Na and Nb. So what we are doing here, we are putting the value of ZAB, okay, we are putting the value of ZAB from here equation 4 to equation 3 first, and then what we are using? We are using the expression of Na and Nb. So we get a rate is Na square sigma 8 kBt by pi mu to the half, and the concentration of A times concentration of B e to the minus Ea by kT. Now if we compare equation 7 and 8, so 7 is this expression, this is again a rate, and 8 is also a rate, okay, expression for rate. So if we compare these two, so we get K is Na times sigma 8 kBt by pi mu raised to the half e to the minus Ea by RT. This is equation 9. Now what are the factors affecting collision frequency? Temperature. Faster moving particles move further each second and collide more frequently. With increase in temperature, collision frequency increases, and so the rate increases. So as temperature increases, collision frequency increases, so rate will increase. Now the concentration, particles that are packed more tightly together collide more frequently. Gases are more concentrated at high pressure than at low pressure. With increase in pressure, the concentration increases, which increases the collision frequency, so the rate increases. So temperature effect, pressure effect or concentration effect we discussed. Then we discuss surface area. So greater the number of particles that are exposed for possible collisions, decrease in particle size increases the surface area, which increases the collision frequency, and so the rate increases. Okay. So energy of activation. So here we considered Ea. We have not discussed anything about Ea. What is Ea? Ea is nothing but energy of activation or inactivation energy. For product formation, molecules must have enough energy for molecular rearrangement. This energy is not the total kinetic energy of the molecules. It's not the total kinetic energy of the molecules, but the kinetic energy component along the line of their centers during collision. So the molecules must press together with at least a minimum energy E naught for the reaction to occur. The difference between this minimum energy and the average molecular energy is called the activation energy. The fraction of collisions where molecules have energy greater than equals to E naught is given by the Boltzmann factor E to the minus E naught by RT. Only collisions meeting this energy criterion can lead to the product formation. Now we discuss effect of orientation of molecules at the rate of the reaction. Only those collisions taking place between molecules in proper orientation and possessing certain minimum amount of energy can lead to the formation of products. Thus, it is important to study the effect of orientation of molecules on the rate of reaction. So collision not properly oriented. Suppose here we are considering NO2, one NO2 molecule here, another NO2 molecule here. When they approach, they are colliding like this. So oxygen atom is, these blue are oxygen atoms. and yellow is the, or orange is the nitrogen atom. So you see the orientation of oxygen is pointing towards N, so collision, so molecules separate, okay. So there is no product at all. Now it will rotate, and then this nitrogen will face another nitrogen like this. So again we are considering NO2 and NO2, they are properly oriented now. So when these molecules they approach each other, they collide like this, and then we get N2O4 here. So we get N2O4 product here. So orientation is very important, okay, orientation of the reaction, or orientation of the reactants. Thus we conclude that the rate of formation of products is not only dependent on collision energy, but also on the relative orientation of the molecules at the time of collision. So at the time of collision, the orientation is very important. Here you see, as we discussed, so oxygen is oriented towards the oxygen of one NO2 is oriented towards the nitrogen of another NO2 molecule. But although there is a collision there, okay, collision is happening here, but there is no product formation. But when N of one NO2 is oriented towards the nitrogen of another NO2, when they collide each other, we get the product formation. So orientation is very important here. So this criteria of specific orientation of molecules at the time of collision is taken into account by multiplying P factors. We are introducing a factor here, P. So P is the due to orientation. The constant P is called the steric factor, usually less than 1. So value of P is less than 1. Okay, so this is the collision factor here. Okay. Then we discuss transition state theory. Transition state theory introduced by Eyring, Evans and Polanyi in 1935 refines collision theory by using statistical mechanics to predict reaction rate. It calculates rate constant via the activated complex and naturally includes the steric factor in its formula, improving accuracy without focusing on collision dynamics. Transition state theory assumes that as two reactants come together, the potential energy increases and reaches a maximum. So when two reactants they come closer, the potential energy increases and reaches a maximum. The maximum corresponds to the formation of an activated complex that can either continue on to form the product or can collapse back to the reactants. Consider a reaction of the form like this. So A and B they form an activated complex AB. So AB is the activated complex, and then it leads to products. So where A and B are reactants that form an activated complex AB, this has that I already discussed, that can collapse back into AB. So it can come back to A and B without going to product P or continue to product P. If the reactants A and B are at equilibrium with the activated complex, an equilibrium constant can be defined as this. So if this step is at equilibrium, or this is equilibrium step, so we can write K, equilibrium constant K is concentration of AB has, or concentration of activated complex, by divided by concentration of A times concentration of B. So the rate of reaction is proportional to the concentration of the activated complex AB at the top of the energy barrier. It follows that the rate constant can be written as K is kappa times nu times K has, where nu is the frequency of vibration of the activated complex along the degree of freedom that leads to the formation of the product. So from statistical thermodynamics, it can be shown that the vibrational frequency is nu is kBT by H, where kB is Boltzmann's constant and H is Planck's constant. The parameter kappa is called transmission coefficient as introduced and is introduced to account for the fact that the activated complex does not always form product. Okay, so kappa is introduced. Okay, it's just that from the activated complex one can get back to the reactant also. Okay, it does not always form product. So the rate constant it can be related to thermodynamics properties through the relation like this. So delta G is minus RT ln K, that we already know, where delta G naught is the change in the standard molar Gibbs free energy of activation. So from equation 10, okay, so this is the equation 10, okay, the rate constant K can be written as this expression. So K is kappa nu e to the minus delta G naught by RT. And we know that delta G naught is nothing but delta H minus T delta S. So delta G naught is delta H naught minus T delta S naught. So equation 11, if we substitute the value of delta G naught in equation 11, we get delta K is kappa nu e to the delta S not by r e to the minus delta h naught by RT. Now, if you compare equation 12 with the Arrhenius equation, we see that the pre-exponential factor A is given by transition state theory is kappa nu e to the delta S naught by R. The activation energy EA is identified as the enthalpy of activation of delta H naught. So, this is the G versus reaction coordinate here. So, it goes like this from here to here and it comes back like this. Okay, so this is the value. Okay, so this is the variation of G with the reaction coordinate.